So the assignment that is due today is 4.5. And 4.5 is on a review of exponential and logarithmic functions. So when we talk about a graph, or let's consider an equation. If I have something like y equals 2 to the power of x, what makes this exponential, this equation exponential, and not something else like linear or cubic or quartic or something else? Why is this? What makes this exponential? The variable is in the exponent. Yeah. When the variable is in the exponent, it is exponential, as opposed to something else like x to the power of 2, which is not exponential, it is quadratic. So when our variable is in the exponent, it is exponential. When I look at a graph, how do I know that the graph is exponential and not something else like linear or cubic or quartic or something else? What tells me that this graph right here is exponential and not something else? Andrew, any ideas? All right, so if it goes up, so if I have something like this that seems to go up, does that mean this is also exponential? What distinguishes this as exponential and not something else? It's end behaviors. What about the end behaviors make it exponential? One side does what? Yeah, exactly. So one side shoots off to infinity or negative infinity, because this is also exponential. So one side shoots off to infinity or negative infinity, and the other side we have a horizontal asymptote. We have convergence on some horizontal line. So I don't know if that's helpful to write out. So the graph is exponential because one side converges on a horizontal asymptote. And the other side shoots off to infinity or negative infinity. And the other side curves toward infinity or negative infinity. And then we know that the equation is exponential because the variable is in the exponent. Exponential because the variable is in the exponent. In this case, the variable is the exponent, but we could have something else like a -1 or something like that. And this would still be exponential because our variable is in the exponent. All right, what about, so we have an equation, we have a graph. What about a table? If I looked at a table of values, such as, I don't know, 0, 1, 2, 3, 4. And then we have, I don't know, 4, 8, 16, 32, 64. What tells me that the table is exponential and not something else like linear, quadratic, cubic. Yeah, so there's some type of ratio, right? There's a common ratio. And in this case, the common ratio is 2. But it doesn't have to be 2. It could be something else, right? It could be 3 or 4. It could even be a fraction. In this case, we have a common ratio of 2, not a common difference. A common difference would be linear. But if I have a common ratio, then that makes it exponential. So this is exponential because we have a common ratio. Exponential, let's use blue again. Exponential because we have a common ratio. Ratio. Yep. So in fact, we could look at this and we could try to determine, a good way of coming up with an equation. What equation is the y equals mx plus b? What is this? Is that linear, exponential, quadratic? What is that? What is it? It's linear. Would that apply to this equation or for this sequence here? No, because these are two different function families. So we're going to try to come up with a function family that represents this sequence here. So I'm going to just rewrite this again. We have, here's my x and here's my y. We have 0, 1, 2, 3, 4, and then 4, 8, 16, 32, and 64. And if I look at this line here, I can represent this value of, of y just by writing, 4. And the next one would be 4 times 2. And the next one would be 4 times 2 times 2. And the next one would be 4 times 2 times 2 times 2. And the next one would be 4 times 2 times 2 times 2 times 2. So if we could think of this as, for the sequence, we could write an equation of y equals 4 times, we see that our common ratio is 2 to the power of what? Does x work? If I plug in that x of 0, does that work? If I plug in 1, does that give me my corresponding y value? Or if I plug in 2, does that give me my corresponding y value? Yes, no, maybe so? So instead of using this y equals mx plus b, what is the equation for this sequence? Or what would be the generic equation? Y equals what? Maybe our 0th term? That's my 0th term. Here in this case, my 0th term is 4 times what? Times my what? My ratio, my common ratio, whatever that is, to the power of what? To the power of x, yeah. Instead of using this equation for linear, we have another equation for exponential. We just use our 0th term times our ratio to the power of x, and then we can write an equation for anything. Any exponential, right? Use this one for any linear and use this one for any exponential. I'll leave that one out there. Now, I don't know what's more common in secondary math 1, but in secondary math 1, I think they give you this equation, y equals our first term times our ratio to the power of, do you remember this in secondary math 1? X minus 1. Was this more common in secondary math 1? Or you could do our second term, which would be r to the power of what? x minus 2. Does that still give us the same answer? Let's use our second term. Let's see if that actually works. So our second term is 2. So I have y equals 2 times r. R is the same thing. It's still that ratio that common ratio. So that would be 2. I'm sorry, I'm using the wrong. This is our term, our second term. Our second term in this case is 16. So I have 16 times 2 to the power of x minus 2, right? I'm making a claim that these are the same thing. Is there a way to prove it? What's our law of x? What's our first law of exponents? What does our first law of exponents say to do? If I have a to the power of b times a to the power of c, how can I put these together? A to the power of b plus c. Can't I separate these in the same manner? So that would give me 16 times 2 to the power of x times, work backward. What do we get? 2 to the power of negative 2. What's our negative exponent rule? If I have a to the power of negative b, what do I do? Yeah, 1 over a to the power of b. So that gives me 16 times 2 to the power of x times 1 over 2 to the power of 2. Or isn't that just 4? Now, because multiplication follows the commutative property, then the order doesn't matter. 3 times 4 is the same thing as 4 times 3. That is the commutative property where the order doesn't matter. So I'm going to rewrite this then as 16 times 1/4 times 2 to the power of x. Well, what's this? That's 4. So are these the same? Are those the same? Yeah, they're the same. So we can use our 0th term times our ratio to the power of x, or our first term times our ratio, our common ratio to the power of x minus 1, or our second term times our ratio to the power of x minus 2, or our third term times our ratio to the power of x minus 3, and so forth. It all works out. Okay, so let's say, I do want to introduce this other number here where we have this number e. Have you heard of this number e before? Yes. What is e approximately? We know pi is approximately 3.14. I'm not doing very well. 3.14. What's e? Approximately what? 2.71. Is that right? Is it 17? Let me check. I'm getting 7.2 maybe. 7.2. Okay. Yeah, approximately 2.72. Why do we know what pi is? What's the point of pi? For every circle, the ratio between the circumference and the diameter is what? Yeah, the circumference over diameter is pi. It's not approximately pi, it is pi. So anytime we deal with circles, a lot of times we have to deal with this pi. All right, so what's the point of e? Let's do an experiment. Has anybody heard of what the point of e is, or is it just a number? If I have an equation of, let's say that we have we start out with $1. Okay, we invest. I think I might not have enough room here. Let's go back up to the top. I'm going to invest $1. So discover the value of E. That's my point. We're doing an experiment. We're going to discover the value of E. I actually think this is one of your quizzes, but I think it's helpful to talk about it explicitly in class. Now you're going to invest $1 at 100%. Oops, that's not how you write 100%, at 100%. So we start out with $1. Now this is going to be our 0th year, our 1, 2, and 3, and so forth. I'm investing $1. Actually, we're just, let me change that. Number of compoundings. Number of compoundings. Compounding, number of times we compound the interest. So let's say that we're going to, so here's going to be 1 time. Now, if I invest $1 for 1 year at 100%, then after a year, I should have how much money? I should have $2. Yeah, I should have $2. So we are going to, this is number of compoundings, and then this will be how much money? So how much money? Okay. And we could use a simple equation of our our 0th term times our ratio to the power of x, right? And so in this case, our 0th term is 1. That's what we're starting out with, times our ratio is if we are growing at a rate of 100%, so it's so that would be 100. So what would that equate to as far as a ratio? If our money grows at 100%, it can't be 1 because 1 times 1 is just 1. So the money hasn't grown at all. The 1 represents 100% of our value times our ratio of 100%. So that would actually be 2. Our ratio is going to be 2 to the power of x. So in this case, we're going to plug in our 0th term, which is 1, times 2 to the power of x just gives us 2. So we get 2. Now, when we talk about compounding more often, we need to use a different equation. Now, let's work through this. Before I give you the equation, let's work through this, this other method first. Let's try to logically consider if we are compounding more than 1 time per year. Oops. So, my word. Okay. I think I'm just too close to the edge. There we go. Now I'm going to compound twice a year. Now let's consider what happens when we compound twice a year. So we're going to make it halfway through the year. So we invest our money in January. Now halfway through the year, June or July, we get paid part of that interest. Now that's still 100% per year, but we're going to get interest halfway through the year, and then we'll get interest again at the end of the year. Let's logically think about this. You have that $1, and then halfway through the year, you get part of that interest. How much of that interest do you get? So we still have that $1, and then halfway through the year, we get interest. How much interest do we get? Did I lose everybody? Yeah, you get half of it, which would be what? You get 50 cents. Yeah, so we'll get 50 cents. We'll get 50 cents. So halfway through the year, we get part of that interest. We get 50 cents. Now at the end of the year, you get paid again. If we're going to compound this, our interest twice. At the end of the year, how much do you get?
compounding the 1.5.
Uh-huh. At the end of the year, how much interest do you get? Point 0.75, yeah, 0.75. You're getting the interest on the dollar, plus you're getting interest on the 50 cents. So together, this should be how much? If we compound twice a year, then how much money do we get? $2 and louder and 25. Yep, we get $2.25. Now I'm going to give you the equation for how to figure this out. The equation for compounding multiple times is this. So I don't know, let's do here's our principal. Here's our principal equals our initial principal times our, we could actually use the same notation that we used before. That's our 0th principal, our 0th term. And then we have times 1 plus r over n. N represents the number of compoundings, and r represents what our ratio is to the power of nt. This is our equation. Now, I used r up here as 2, but r really is 100%. So I'm just going to throw in our values. Let's make sure that this equation still gives us the same answer. We have $1 plus, times 1 plus r, our rate is 100% over the amount of times we're compounding, which would be 2 to the power of 2 times 1. We're just doing this for 1 year. Does this still give us the same number of 2.25? Does anybody have a calculator? Yes, no, maybe so. What's this piece here? Is that 3? Is that 3.5? 3 halves? 3 halves, I mean, 3 halves. Yeah, so it should still give us this 2.25. Right, using that same equation, what happens if we compound, don't put your calculator away. What if we compound 4 times a year? So that would be every quarter, right? So you invest your money at the beginning of the year, you get paid in March, and then in June, and then in September, and then at the end of the year. Using our equation, how much money would we have at the end of the year? Or did everybody put their calculators away? If we compound 4 times a year, we're plugging in 4 here and 4 here, and this is still 1, and this is still 1. What is it? Okay, so we get 2.44. All right, so you get, if we compound every quarter, instead of $2, you're getting $2.44. Why are you getting more? Explain to me why we're getting more than, and we're still getting 100%. Our interest is still 100%, but why are we getting more? Because we're getting paid interest on some of this interest, right? Because we're getting paid interest on some of this interest. All right, what if we do this instead? What if we compound every month. So how many times are we going to compound a year if we compound every month? Yeah, so this will be 12. Using our equation, what do we get? We get 2.61, yeah, 2.61, yep. What if we compound every day? How many times would that be compounding per year? 365, okay. Using that same equation, how much money would you get if we compound every day? 2.71, okay. What are we converging on? When we compound more and more, what do we converge on? Yeah. Riley says, what if we compound infinity times? If we compound infinity times, we actually get E. We actually get the actual number if we compound infinity times. You can put a larger and larger number in for n, and you get closer and closer to the value of E. So what's the point of E? Why do we have this value E? It's the idea is when we compound continuously. And there's some real world applications where we compound continuously. What about, for example, the radiation at Chernobyl? The radiation there, it's detectable how much radiation is there now, and we can make predictions on how long it's going to be before Chernobyl or that whole area, Pripyat, will be safe for human habitation again. And those kind of equations that are created, they are not compounded yearly. They're not compounded twice a year. They're compounded continuously. And so we need to use, when we talk about something being compounded continuously, then we have to use this value E. In fact, we end up with a new equation when it's compounded continuously. So the equation for compounding continuously is, we'll use P as our principal, and then times our initial principal times E to the RT. So we are literally going to use that ratio, that common ratio is going to be E. That E, that value will allow us to have to be compounding continuously. Not compounding every half second, not compounding every quarter of a second, compounding continuously. We have this value E. So that is, I like to think of it as just P E to the RT because it spells PERT. Now, when I was your age, a popular shampoo was PERT, and it made your hair really soft, and it also stripped your hair. So I don't think it's really popular anymore. Probably doesn't even exist anymore as far as I know. But just a helpful way to remember this equation is PERT, PE to the RT. What is the point of E? What is the point of E? Why do we have this number E? To compound continuously. This is actually going to be a really important value when we continue on with calculus. You will see E quite a bit. And so I want you to understand where E comes from. And it comes from this idea of compounding continuously. So we're going to move on. This is one of my favorite equations. And if I used this example before in class, I do apologize, but I just think it's, because these are real numbers, I think it just makes the problem so much more fun. So here's my example. A population, here's my example. A population of mice will grow at a rate of 20% per week under ideal conditions. Under ideal conditions. That means that there's enough water, there's enough food, there's enough space, there's no disease. The population of mice will grow at a rate of 20% per week. Write an equation for a population of, write an equation for the growth of a population of 100 mice. I want to write an equation for the growth of 100 mice. What's my equation? Y equals our 0th term times r to the power of x or t or something like that. I'll use t for time. Are we going to use e in this case? Do the mice grow continuously? No, they don't grow continuously, so that would be improper to use the equation with e in it. What is f of 0? 100. What is r? Louder? 1.2. Yeah, we have to account for the 100 mice plus the 20%. So together that would be 1.2. 1.2 to the power of t, where t is in number of weeks. You guys good with that? You comfortable with that as our equation? How many mice will we have in 5 weeks? How many? Let's use below. How many mice in 5 weeks? Yeah, so we just take this 5, we plug it into our equation right here. So that would give us y equals 100 times 1.2 to the power of 5. And you said it's approximately how many? One more time? 248 mice. Okay. When or how many weeks before we have 1 million mice? How many weeks before we have 1 million mice? We could do a guess and check. How would we do it without a guess and check? Yeah, we make y equal to 1 million. And then solve for t, right? How would we solve for t? We divide by 100 to both sides. And dividing by 100 is easy because now we just knock off a bunch of zeros. And so that gives us what, 10, is that 10,000? 10,000 equals 1.2 to the power of t. And then what? Yeah. Now the inverse of an exponential is a logarithm. The inverse of an exponential is a logarithm. So let's write this down. This is super, super important. So the whole point of a logarithm, the inverse of an exponential is a logarithm. See if I can clean that up a little bit. Okay. Now, one thing that inverses do is they undo each other. And graphically, let's just write this out. If I have, we'll say this is y equals a to the power of x. And the inverse of an exponential is a logarithm. So an inverse graphically is a reflection across what line? Y equals x. Yeah, so we have to have some graph that's a reflection across this y equals x. That gives us something like this. And because the whole point of a logarithm is to be an inverse, we will call this y equals log base a of x. They're inverses. What's the inverse of a quadratic? What's the inverse of a quadratic? A square root, yep. An inverse of a quadratic of x squared is a square root. What happens when we take a composite function of the two inverses? If I take x squared and I put this inside, that's what makes a composite function, then that gives me what? X. What if I do the other way? What if I take this and I plug that into this function here? So that would give me the square root of x squared. What does that give me? X. Now that's the nature of inverses. They undo each other. They undo each other and we're just left with this x. So following this line of reasoning where inverses undo each other, if I take this value here and I plug it into here, then what should I get? X. So if I have a to the power of log base a of x, this literally became the exponent. Then this has to be x based upon what inverses do. Now, if I take this value here and I substitute that in for x here, so that I have log base a of a to the power of x, then based upon inverses, this has to be what? It has to be x. I'm not going to say that these are rules. I'm going to say that this is literally the definition of a logarithm. Right here, this is literally the definition of a logarithm, that they undo each other. A logarithm wouldn't exist without this idea where if the composite function of an exponential function and a logarithm would give you x, would undo each other. That is super, super important. So we're going to use this idea to try to undo. I'm just going to copy this here. If I'm going too fast, let me know. We're going to use this idea to solve our problem regarding how long it's going to take before we have 1 million mice. Okay, there, you good? Cool. I'm going to go back up here. Just going to drop this. I'm going to call this the definition. It's really the definition of a logarithm. So looking at this definition here, is there some way that I can use this definition to isolate this t value so that I have my answer over on the left-hand side. Oops. Yeah, so we're going to try to use, we're using this piece here, right? We know that if we can rewrite this as log base a of a, then it will leave us with the exponent. So I'm going to use, we're going to use log base what? 1.2. We're going to, yeah, the a values have to be the same. Whatever we do to one side, we have to do to the other side. So I have log base 1.2 to the other side as well. What does this become over here on the right-hand side? It's just t. It just gives us the exponent. So that just gives us t. Now, using your calculator, this is important. Remember, for the AP test, half of the test is with a calculator and half is without. So you need to know how to do this with your calculator. With a TI Inspire, I would do alpha window. TI-84. A TI-84 do alpha and window. If you are using a TI Inspire, then I think it's on the left-hand side in yellow, it says log. So you have to push the second, and then I think is it 10 to the power of x or something like that? Okay. So what does that give you when you put that in your calculator? What do you get? 50.52. Okay. What are these? What are my units? Yeah, this is how many weeks, right? That's how many weeks. So we're going to that. My units are weeks. How long is a year? Isn't it 52? Do we have 52 weeks in a year? That's crazy. Under a year. It would take under a year for a population under ideal conditions for a population of mice to grow to be 1 million mice. That's crazy that they would grow that fast. Nice. Okay, we're good? We're going too fast? Still copying? Okay.
I think it's like log 1.2. Log in this case 1.2. Or I'm sorry, log of 10,000 over 1.
You're saying,
is that
so this is Kate is asking if we have log base 2 of say 8, right? I can rewrite this how?
log of 8 over log of 2?
Yep. What base is this over here? Log base what? Yeah, base 10. This is called the change of base formula. This is called the change of base formula. It allows you to do that. But your calculator allows you to do. In fact, my calculator, when I was your age, there wasn't a calculator that did, the anything base. So we had to learn the change of base formula, which is also the same as this. What base is this? What base is this? It's E. This is called the natural log. You can say ln if you want to, but it's the natural log. This is the natural log of 8, which is really the same thing. This is the same thing as log base E of 8 over log base E of 2. Do you see in your calculator that button? Okay. It's the same as log base E. Okay, we're going to talk about the properties of logarithms. Everybody good? Okay, I'm not going to call this the property. These aren't properties. This is literally the definition. Now, using our definition, we've seen certain patterns. And that's what I want to talk about next. Based upon our definition, do I still have that? Okay, based upon our definition, we've seen patterns. Based on the definition of logarithms, we have seen the following patterns. We have seen the following patterns. Okay. One of the patterns that we saw, this is from secondary math 3 from last year. One of the patterns we've seen is when we have log base b of x times y. This pattern allows us to expand. Have you seen this before? It allows us to expand to what, Josh? Yeah. Yep. We also have log base b of x over y. And the pattern we've seen with this one is what? Log base b of what? X. Nice. Log base b of y. Yep. And then the log base b of x to the power of y. What about this one? Louder? Yeah, doesn't it allow us to move this to the front? We get y times log base b of x, which is sort of interesting because that becomes a vertical stretch. What used to be an exponent becomes a vertical stretch when we consider the function. Crazy, crazy stuff. Now, if you wanted to, you could think of this as, like our first one here. This looks, because logarithms are the inverse of exponentials, maybe it's not so surprising that the first one sort of has a feel of this idea when we have b to the power b to the power of x times b to the power of y. We rewrite this as b to the power of x plus y. That's sort of the same kind of feel to it. We're multiplying. And the next one, this second one sort of has a feel similar to if I have b to the power of x over b to the power of y, then I can rewrite this as b to the power of x minus y. I'm not sure what the other one would be. Maybe b to the power of x times b to the power of x to the power of y would give you b to the power of x times y, maybe. Maybe. What about if I have log base b to the power, log base b of 1? What is that? What would that give me? It's not going to be b. If I had log base b of b to the power of b, that would be b. It is 0. It is 0. Let's look at this, which one? This one right here. If we have log base a of a to the power of x, then they undo each other, and I'm left with my exponent of x. What if I used our 0 exponent rule? Couldn't I rewrite this as log base b of b to the power of 0? Because isn't b to the power of 0, isn't that 1 based upon our 0 exponent rule? And then based upon our definition of logarithms, then our exponent becomes our answer. So the answer would be 0. Yep, the answer is 0. If I have log base b of b, what was that? What is it? Yeah, it's 1. Yeah. Yeah. If I have log base a of a to the power of x, our exponent becomes our answer. So here I have log base b of b. Well, that's to the power of 1. That's implied to the power of 1. So our answer is 1. Yeah. And log base b of b to the power of n. Louder? Yeah, just n, yeah. And I'd argue that that's not really a rule. That's our definition. Are the definitions rules? Maybe they are rules too, but when you define something, you say, and then all of the other math comes from that definition, then I think it feels like the discoveries are the rules, and then this here is our definition. You can disagree with me if you want, but nevertheless, this is something you have to learn. You need to learn all this. What's the main idea today? Yep. Have we done any calculus? No, we haven't done any calculus. What would make it calculus? What would we have to do to make this calculus? What's that idea that we've been doing this whole time? Yeah, finding the derivative, finding that instantaneous slope. Have we found any instantaneous slopes? No, this is not. All of this is secondary math 2, secondary math 1, secondary math 3. It's all of them. Secondary math 1, 2, and 3. We've done all of those concepts that you've discussed in previous maths. That's made up today's instruction. And that's your homework doesn't have calculus either. Your homework is a review of logarithms and exponential functions. So let's do another one. Let's do, let's say I'm going to zoom in. Here's our example. I have an equation. The equation is P of T equals 92,500 times E to the power of 0.05 T. Now, I don't want to write out all of the prompt. I'll just read it to you. I just think it can become, it's just a little bit too much. The prompt is, in 1980, the population of a city was 92,500. The population of a city at a certain time was 92,500. So what does this number here represent? The population of the city at the initial date, right? That's the population, that's our 0th term, right? And then this E means what? Continuous growth. What's our equation? Remember PERT? Remember our equation, PERT? PERT. So our E is, it means we have continuous growth. And then what does this mean here? What's the 0.05? What does that represent? That's the rate of growth. What is the rate of growth as a percentage? 5%. Yep, we move the decimal point 2 spaces. We see that we have a population growth of 5% per year. And so here, this is our equation. I'm just going to go ahead and get rid of this part here unless you want it. So this is an equation that represents the population growth per year of a city. And I want to know when the population, I want to know, this is my question. When will the population reach 180,000. And I suppose the prompt is a little bit more interesting because it says the question is there's a part of the question says that the hospital can only accommodate 180,000 patients. And so we have city planners that need to make a prediction on when we need to start building onto the hospital. So once we've reached the 180,000, once the population has increased to that point, now let's make sure we understand this, that, you know, of course, the hospital couldn't accommodate this many patients, 180,000 patients, but we do have we have lots of tables and charts from experiences in the past to determine, based upon a size of a city, how many patients a hospital should be able to accommodate. So do you want some think time? Or do you have no idea how to do this? Emma, what do you think? Do you want some think time or should we just do it as a class? Yeah. So when will the population reach 180,000? Well, what the heck do I do with this number here? Put it where? For T? What did you say? Put it for E? Yeah, so E's not a variable, right? And so we're going to replace the P of T with this number 180,000. So I have 180,000 equals 92,500. I'm just copying everything else from the equation up here. Not adding anything new here. Ooh. Emma, now what? So we want to end with T equals something, right? And that will tell us how many years until the population reaches a certain amount. So what do I do to do inverse operations to get T by itself? I'll give you a hint. This is times. Not yet. We're doing inverse operations. Yeah, we're going to divide. We're dividing by that 92,500 to both sides. So let's divide by this 92,500. And of course, 92,500 divided by 92,500 gives you 1. So I have one of these e to the power of 0.05 t. And what does that equal? Louder, please. Okay. I'm a little bit nervous about rounding errors because, well, rounding errors are things that happen when we round before our final answer. So if I have 180,000 divided by 92,500, I'm getting a pretty big number. I'm just going to put all as much as I can in there, just so I can avoid a rounding error. Yeah, just leave it like this. Yeah, I like that. Let's do that. Yeah, I agree. Yeah, so you left it this as it. So when you wrote this, when you figured this out, what was the fraction?
72 over 32.
72 over 32. Okay. Now what? Again, the goal is to get T equals something. Do log base E. Now we have a special button that does log base E. What is it? Yeah, we're going to do ln. We're going to do ln to both sides. These are inverses. They undo each other. And we're left with 0.05 t equals whatever that is. We can leave it as a, fraction. We can leave it just like that, so that we get a perfect answer without a rounding error later. What would be the next step to get t by itself?
72 over 37.
Uh-oh. Okay, it's possible. Let's do math. 72 over 37. Yeah. I might have misheard Riley. So this is 72. Thank you. Okay. So again, my goal is t equals something, to get t by itself. What's the next step? Yeah, this is time. So we're going to divide both sides by 0.05. 0.05. Now we can finally round. Throw all that into your calculator. How many years? $32.30.31.
13.
Oh, I'm completely hearing you wrong. 13.31. Do I have confirmation? Does that look right? Okay. According to the problem, the answer then is going to be 13.31, or about 13 and a third of a year before we have to add on to the size of our hospital. All right, let's do another one. How much time is required for an investment to triple in value if the interest is earned at 5.75% compounded continuously? So how much time is required for an investment to triple in value if interest is earned at 5.75% compounded continuously? Sam, do you remember the equation for continuous growth? Isn't it that shampoo? I don't even know if they sell Pert anymore. I don't know if that's.
I think so, if that's the results.
No, it was awful to your hair, but you know, for me, I cut my hair all the time, so it's not like a big deal. Even had Pert Plus. I don't know if that's even a thing anymore. Pert Plus. Oh, they still do have Pert. Yay. Pert. Okay, so I guess if you want your hair stripped, Buy some pert. Okay, so how do we remember this equation? Pert, it's pert. PE to the RT. PE to the RT. We're going to use our equate. So P equals our initial amount, PE to the RT. Are you guys stuck? Does it matter what these guys are here?
Kind of.
Do they, if I'm worried about tripling?
Well, when.
Make something up.
If you want to solve for that, wouldn't you do P times 3 to represent it tripling?
Yeah. Oh, P, if we took this divided by this, we should get 3,
Yeah.
right? You could throw in a number. You could say, well, let's reason that if I started out with $1,000, that would have to grow to be $3,000 if we are tripling. Or we could say it's, $200, and then if we're going to triple it, 2, 4, 6, that would be 600. Does it really matter what those are?
No.
What should this divided this? I should say this. No, this divided by this. What should that give me? It should give me 3. Should always give you 3. Okay, so that's going to give me 3 equals E to the RT. Anything else we can fill in here? All right, my rate. What is my rate? Yep. And what's the T? Well, that's what I'm trying to figure out, right? How much time? So that's my T. That's what I'm trying to figure out. Okay, how do I figure this out? Yeah, we do ln. We're going to do ln to both sides. These are inverses. They undo each other. And I'm left with ln of 3 equals 0.0575 t. Now what? Yeah, divide both sides by that 0.0575. And that gives me what? $19.1. Yeah, 19.1 years. Take you 19.1 years for your money to triple. At that 5.75%. It'll take 19.1 years. Okay. Any questions about today's instruction? We still have 10 more minutes. I would love to go through the flashcards with you. That's how we're going to learn. We learn through repetition. We learn everything through repetition. We need to go through these. I know that we've added a bunch of new cards. We don't have that many more flashcards that we have to add, but we do have to get used to these, especially when we talk about integrals. We need to learn how to do these backward. So, great. So we have the inverse. I'm trying to find the derivative of the inverse of tangent. What is it? Is it going to be negative or positive? Positive because it's not a cofunction. Good. It's going to be positive. It's going to be 1 over what? X squared plus 1. Good. Okay, let's do the next one. I want to know the derivative of sine of x. That's cosine of x. Good. I want to know what the derivative of the inverse of cosecant of x. What that is it going to be positive or negative? It's negative because it's a cofunction. So it's going to be negative what? Oh, this is the ugly one, huh? 1 over So it's negative 1 over the absolute value of x. The square root of what? X squared minus 1. Good. Yep. Yeah, that one's probably the hardest one. That one's probably the hardest one right there. Okay, what is the derivative of cotangent of x? Yeah, it's a cofunction, so it's negative. Negative one more time. Cosecant squared of x. Good job. Nice. Okay, next one. What is the limit as x approaches 0 of sine of x over x? It's 1. Good. What is the derivative of tangent of x? Secant squared of x. Good. What is the derivative of the inverse of cosine of x? Yep, it's negative because it's a cofunction, so negative 1 over the square root of what? 1 minus x squared. Okay, there we go. What about the derivative of the inverse of cotangent of x? Yeah, this is a cofunction, so it's negative. So I have negative 1 over x squared plus 1. Yep. Okay, next one. What is the derivative of the inverse of secant of x? Yes. All right, yeah, so this one's the other more difficult one. This is going to be positive because it's not a cofunction, so it's 1 over the absolute value of x times the square root of x squared minus 1. There you go. Okay, what is the limit as x approaches infinity of sine of x over x? It's 0. What is the derivative of secant of x? Yeah, secant of x times tangent of x. Good job. Secant of x times tangent of x. All right, what is the limit as x approaches infinity of cosine of x over x? 0. 0. What is the derivative of cosine of x? What is it? Negative sine of x. Nice. Thank you, gentlemen. Right, what is the derivative of cosecant of x? Yeah, negative cosecant of x times cotangent of x. Good. What is the derivative of the inverse of sine of x? Yeah, is it going to be negative? No, because this is not a cofunction, right? Well, my cofunctions are cosine, cosecant, and cotangent. This is not a cofunction, so it's not going to be negative. So one more time, what's the derivative of the inverse of sine? Yep. Yeah, 1 over the square root of 1 minus x squared. Yep. Okay, that's it. If you have not learned these yet, I highly recommend that you go to at the very top of the page, the first module under question board. I have the first 2 videos, the beginner level or the intermediate level. The intermediate level has all those inverses. The beginner doesn't have those inverses yet. So if you haven't learned the first ones, I suggest that you work on the beginner level first and then the intermediate before we start doing the advanced. Now I still have 4 more minutes, so I would like to go over another important concept that we need to remember. I have not added these to my flashcards. You may want to add these to your flashcards if you want to, but these are things that you are still expected to know for the test, the AP test. Even if you're not planning on taking the AP test, I still expect that you will learn these, especially if you're planning on retaking this class in college or moving on to the second level calculus class. So I want you to remember the power rule. The power rule, if I have y equals a times x to the power of n, the power rule says that the derivative is going to be what? A times what? Yeah, oops, I'm not happy with A. A times N. N minus 1, that is called the power rule. Good. We also have what is called the product rule. The product rule, it means that I have a function times another function. My function is made up of the product of two functions. So using the product rule, then my derivative is going to be what? Yep. So it's the first function times the derivative of the second plus the second times the derivative of the first. All right, besides the product rule, we also have what is called the quotient rule. Quotient rule. I'm not being consistent with my capitals. All right, the quotient rule is if I have a function made up of the quotient of two functions, then my derivative is going to be low d high minus high d low over low low. Okay, what are we missing? What's the one we haven't done? We've done the power rule, the product rule, the quotient rule. What are we missing? We're missing the chain rule. What's the point of the chain rule? So the product rule, the point of the product rule is when we have a function times another function and we're trying to find the derivative. The quotient rule is if we have a function divided by another function, we're trying to find the derivative. What about the chain rule? What's the point? Well, we have a function inside of another function. So I have y equals f of g of x, and I want to find the derivative of that. What do I do? The derivative of the outside function times the derivative of the inside function. Yep, that's how you calculate it.